Lecture 16, Real-Time Scheduling Algorithms. Given our understanding of scheduling algorithms in general, and an understanding of what makes real-time system scheduling at least a little bit different from just regular scheduling, we can consider at this point some other scheduling algorithms that will work for a real-time system. Right? We know why, after some examination, like a regular scheduling algorithm isn't sufficient, and we've considered the idea that using the wrong scheduling algorithm results in failure to meet our goals, failure to meet our deadlines. And we covered the idea already of timeline scheduling, right? If everything is predictable and orderly, then making a schedule, making a plan, and saying, okay, we do this in this order, that works, but it's not always going to address sort of the real world. Right, we know that the life that we live is not full only of periodic tasks, but there are in fact frequently aperiodic and sporadic tasks and things like that. So we need to consider those. And for now, we'll go back to the uniprocessor world because it's just much simpler to start with, but eventually we must indeed add in the complexity of multiprocessor real-time system again. But for now, we'll start with the uniprocessor because it's easier. Okay, so I want to talk about first the earliest deadline first algorithm. And I'm going to assume that the earliest deadline first approach to the world is probably at least somewhat familiar to you as a student. If there is an assignment that's due today, and an assignment that's due next Tuesday, and then an exam next month, well, chances are you are going to prioritize on the basis of which one of these has the soonest deadline. And so if you follow that, you would focus on the assignment that's due today because, yeah, it has the soonest deadline, and so you really need to get started on it if you intend to finish on time, now don't you? And realistically, the principle is the same for the computer, right? So if you have an assignment that's due today, right, you do that first, and after you complete it, you decide what to do next. And maybe it's the next Tuesday one, but maybe a new task has arrived in the meantime. If that's the case, then, well, yeah, you will just get started. Whatever it is you're going to choose, you're going to choose. And the same is true, as I say, for the computer. It will look at the deadlines of the tasks, and it will choose whichever one has the soonest deadline. If there is a tie, then you have to choose between them, and random selection is possible. Maybe there's other criteria that you can use to differentiate between the tasks. Whatever it is, you pick something, and then you do it, right? Now, it is noteworthy that earliest deadline first is what we would call an optimal algorithm. And I don't mean optimal in the sense that like it's always the best and there's no way you could possibly do better or anything like that. What it means is that if there is a possibility to schedule all tasks such that all deadlines are met, then this algorithm will find it. The notes link to one of the textbooks that has a formal proof of why this is optimal and proof that it will in fact solve it. But I've left it out here because I don't think we need it. But if you need some convincing, sources linked. So if a task is executing and another task arrives with a sooner deadline, then the currently executing task will have to be preempted to make way for it. So the currently executing task should be suspended so that this other one can continue. And that does mean that preemption is necessary to make it work, right? A task could arrive that is more urgent, i.e. has an earlier deadline than the currently executing one. And that's okay. And that happens in real life too. That sometimes you get a call while you're in the middle of something that says, hey, I really need you to take care of this. And you're probably familiar with this also from a co-op term. Where you're working on some particular assignment, and then you attend a planning meeting, and after the planning meeting, somebody tells you actually you really need to drop what you're doing and focus on this thing, which is more important, and that's fine. And that may mean that a periodic task is preempted by an aperiodic or sporadic task. That's okay as well. It's just about which is sort of the which is the most urgent, and urgency is determined by deadline. right? So how do we organize ourselves to work with this? Well, one idea is a priority queue. And a simple view says that priority is just determined by the deadline, but maybe that doesn't account for task type. So a soft real-time task may have a sooner deadline than a firm or hard real-time task. Is that a problem? It's only a problem actually if we're overloaded, right? If the system is not overloaded, then we can do all the tasks, and it doesn't matter if the task that's got the soonest deadline somehow is a soft real-time task, because if there's time to do it all, then, well, it doesn't matter that much the order in which they complete. I mean, it can matter, it can be important, the order in which these things complete, but for the most part, as long as everything gets done, we're pretty happy with that. And yet, right, what if the system is in fact overloaded? What then? Well, if the system is overloaded, then we have to make some choices, don't we? Generally, good system design means that overload is not an issue, but reality is not always that nice. And if that's the case, we're gonna have to make some choices. Do we skip the soft real-time task? Do we start it but cancel it if we run out of time and things just get more dire? Let's actually come back to that decision after we've talked about sort of a couple of other things. We'll also talk about in this context deadline interchange. And deadline interchange is based around, well, it's analogous to priority inversion, but comes from a different kind of problem. The deadline-based approach is subject to this priority inversion-like problem where task A has locked a mutex and task B arrives that also needs that mutex, but it has a sooner deadline than A. Right? Task A would be preempted in favor of B until B gets blocked. And if there are other tasks, C, D, and E, that also want this resource, the mutex, process A could be waiting a long time before it is able to proceed. In fact, it could be waiting so long that task B misses its deadline. Right? And similar to the priority inversion case, to solve this, right, we need to make sure that A can continue executing such that it will release the mutex and unblock B. And the solution is effectively the same. That's why it's called deadline interchange, which is we would assign A new deadline, specifically the soonest deadline from all of the tasks that are waiting for it. And that looks kind of like priority inheritance, right? Where priority inheritance was a lower priority task gets its priority increased based on who is waiting for it. Now, a task that has a relatively longer deadline gets a relatively sooner deadline based on who is waiting for that as well. So that makes some sense, and you can see why this addresses the problem in a relatively straightforward way, but also in a way that we are at least passingly familiar with from our discussion of priority inheritance. It's a similar problem, so it's not weird that the solution also looks pretty similar. And then there is least slack first. Similar algorithm to earliest deadline first, but least slack first. Actually, no shade on Slack. I much prefer it to Microsoft Teams, let's say that. But this is not the kind of Slack that we are talking about. No. Slack is how much time a task can wait before it must be scheduled to meet a deadline. So if a task will take 10 milliseconds to execute and its deadline is 50 milliseconds away, there are 50 minus 10 equals 40 milliseconds of slack time remaining. That is to say, we must start the task before 40 milliseconds are expired if we want to be sure that the task will finish. This does not mean, just for the record, that we necessarily want to wait those 40 milliseconds before starting the task, even though lots of people will do something on that basis. If you know that the task is going to take an hour, leaving it to an hour before the deadline, it is an option, but it's not one that I personally would choose. I think you know that because we've been over this a couple times, including even in the discussion at the beginning of the term around how you should approach the labs, and my very fun 2A experience with someone who had an incompatible working style. But all things being equal, right, we want tasks to start and finish as soon as possible when we are scheduling them on the CPU. So we're not going to just do nothing while there are tasks that are ready just because they have lots of slack in them. But the purpose of calculating slack is sort of working out what tasks are in the most danger of missing their deadlines. And knowing that helps us to figure out how we should prioritize them. Because a task that has lots of slack in it, listen, we can put it off a bit. We need to deal with things that are more urgent. A task that really doesn't have much slack, if any at all, has to be scheduled as soon as we can because, it is already in great danger of missing its deadline. And so our goal effectively is to not miss any deadlines if we can help it. And slack is just a measure of how close a task is to being in that bad state. So that's not super different, honestly. A queue where a priority determines the slack makes for a reasonable implementation. But yeah, it's not really that different from earliest deadline first. It's really just calculating things ever so slightly differently based on slack time instead. So I want to take it to a new strategy, and the new strategy is called rate monotonic scheduling. Sounds like rate monotonic sounds kind of like a band, I suppose, if you think about it. Comment below what kind of music you think they play. But unfortunately, something like earliest deadline first, the name does a very good job of explaining what it does and how it works. But that's not true for rate monotonic scheduling. So we have to break it down a little bit. We consider the rate monotonic algorithm because something like earliest deadline first or least slack first is based solely around the idea of deadlines, but it doesn't care at all about priorities outside of that. And maybe you actually care about priority more than we would think. So rate monotonic scheduling is based around the idea of assigning a task a priority based on its period. So tasks that execute more often are given higher priority. There's a theory behind this that says tasks that have a higher frequency effectively require more attention or more frequent attention and therefore need a higher priority. So each task will be assigned a priority number based on its recurring period, and this priority does not change at runtime. Right? Higher priority tasks should preempt lower priority tasks as needed. But the thing is that this is not an optimal algorithm in the sense of optimality that we discussed earlier on. What do I mean by that? It's possible to fail to schedule things in such a way that all tasks meet their deadlines, even if utilization is less than 1. And if you remember from the earlier discussion about utilization, right, it's the periodic tasks as calculated with their periods and their execution times. And if execution is less than 1 and we have an optimal algorithm, we can be certain that we will in fact find a way to schedule them all. But rate monotonic is not optimal. There is an example here from textbook where if we have 3 recurring tasks and those tasks are described here by their worst case execution time and their period as 1, 4, 3, 7, and 3, 10. If we try to schedule these, we will in fact find that the third task will fail to meet its deadline. Why does that happen? Okay, well, if we go through it, right, we schedule it, so task 1 runs, then 2, then 1 again, then 3. Okay, makes sense, and so far, so good. But if we continue, task 2 runs, then it gets interrupted by task 1. So task 1 runs to completion, and then task 2 resumes, and then task 3 misses its deadline. All right. A little easier if we sort of illustrate it as opposed to me just talking you through it, right? But the first round, task 1 runs, and it runs for the 1 time unit, and then task 2 runs for 3 time units, and then task 3 will run again. Okay, task 1 runs, then task 2, then task 1 again. So we're up at 4 time units, and then task 3 will run. And we're doing okay. But yeah, then task 2 runs, gets interrupted by task 1 again, and task 3 will miss its deadline. But utilization is less than 1, because 1/4 plus 3/7 plus 3/10 is equal to 137 out of 140, which is strictly less than 1. So, earliest deadline first would have been able to schedule this such that all tasks meet their deadlines. Right, there would have been some back and forth, and there would have been some cases where the third task gets a higher priority because it's in danger of missing its deadline, but it's totally possible because an optimal algorithm would find it. So, oh dear, this is embarrassing. Okay, so I mean, how do we know if it is actually schedulable in a rate monotonic scheduling system? Well, there is a test. And the test is mathematical, so okay. It turns out this test is very difficult to do dynamically in real time. So we have to use a less precise formula for calculating it on the fly. Right? If we know exactly all tasks in advance and everything, and so nothing ever changes, I mean, we probably don't choose rate monotonic scheduling, because why would we need to? Because we could just make a timeline schedule. But if you want to do this dynamically, right, we have to choose a less precise formula that looks like this, right? And there's, again, linked in one of the textbooks, some formulae and some proofs that show why this is the way that it is. But effectively, what we are trying to calculate is the sum of 1 plus all of these tasks, worst case execution times divided by their period, must be less than or equal to 2. So if we exceed the value here of 2, it is possible that we will not be able to complete all tasks, and we won't be able to schedule it appropriately. But I want to highlight at this point once again that just because it's not possible to guarantee that all deadlines will be met, that's not a guarantee of failure, right? Like, uncertain success is not certain failure. There is a possibility that we can actually schedule it, particularly because everything is a worst case time, and so things may be better in reality than predicted by using this calculation. Now listen, I don't want to travel on an airplane where we said, I'm sure it'll be fine. I do want to be reassured that they've actually proven that success is certain, but it is important to note that even if you do this calculation, it is possible that we can succeed even if the calculation says success is not guaranteed. Okay, so that is kind of complicated to do. And I also want to just briefly mention there exists a variant of this called deadline monotonic scheduling, in which case priority is assigned based on deadlines. It's really not that interesting or different, although it is hypothetically possible to come up with some examples where rate monotonic would not find a good solution, but deadline monotonic could actually do it. But it's interesting as a subject, both rate and deadline monotonic, and you can see sort of they have a history and have been used in the past, but they're not optimal, so it's kind of not what we would choose, is it? So I want to present a different idea. And a different idea is, well, quite radically different at this point, because we'd like to a certain extent base it on the idea of the earliest deadline first approach, and we would like to support multiple CPUs. So a task with a soft deadline can be challenging to schedule in the earliest deadline first approach, just because of the fact that it's hard for the scheduler to know in advance whether a particular task is hard or soft real time. And one way that you could solve that is by saying that hard real-time tasks always have priority. They are always going to execute before the soft real-time tasks. But that might not be entirely what you want, and that might not be optimal. Okay, so what can we do instead? Well, this idea was introduced sort of in research quite some time ago, like 1995, and it's been growing and expanding throughout the literature for quite some time. And it's based on the idea of, well, what is called a polling server. And the way that I want you to think about a polling server is it's a little container in which aperiodic tasks occur. The server itself is a hard deadline periodic task with a fixed execution budget and a deadline equal to its period. So every time this task runs, you can think of it in a way as being like a little container or Trojan horse for aperiodic tasks waiting to run sequentially. If there's too many aperiodic tasks or they otherwise take too long and they do not finish, those aperiodic tasks just carry over to the next time that the server runs. If there's not enough aperiodic tasks and there's time left over, just end the server execution, throw away the extra time, and let something else run. Okay, so yeah, the whole idea basically is that the aperiodic server is like reserving time for these aperiodic tasks, but we're going to schedule that time as if it is a periodic task. So here's sort of my analogy for this, and it's lunchtime. Okay, so the question is, do you have to use your lunchtime, your lunch break for eating lunch? Well, no, right? You're at work and it's an in-person, in the office kind of job, and so you have to take a lunch break. Okay. You can do whatever you want in your lunch break within reason, and you don't have to use this period of time solely for eating, right? You can use it to do other tasks that you want to do or you need to do. So you can go to the bank, right? You can go shopping, you can shop online on your phone, whatever it is. But the lunch break task is important in the sense that you can't skip it or reschedule it indefinitely, right? Like on my first co-op term, they said, okay, you have to take this much time for lunch, and it can be between this time and that time. Okay, that's fine. At one point, they said you can't schedule your lunch break at the end of the day, so you can go home an hour early. All right, fine, I guess. Right, but lunch break, you have to take a break at some point during the designated time. But when it is lunchtime, it's your time to do with whatever you want. Right, and that's the kind of thing that we're thinking about for these aperiodic tasks. And so these aperiodic tasks, it's a chore, a thing that you want to do or need to do or something like that. And it takes place inside this little container, that container being lunchtime. And the lunchtime itself is a task in your schedule, like you put it in your calendar, and I take lunch from 11:30 to 12:30, and that is an equally important item to some extent to other tasks that exist in your schedule as well. So that's the idea of the aperiodic server. It's this reserved time for doing this thing. You could also think of it as, if you wanted a different analogy, like reserved time for doing household chores. You fill it in with whatever chores there are to do, wash dishes, do laundry, vacuum, whatever it is, you choose which ones they are, and if you run out of time, well, it's time to go back to work. And if you have extra time left over, well, do with it what you will, throw it away, and do something different instead. Now, we can have different servers that work on different kinds of tasks. And so you don't have to put everything into one single server. You can have different containers for different things. So higher priority tasks go in one server, lower priority tasks in another one, and they're scheduled differently with different execution periods and deadlines and stuff like that. So in the lunch break analogy, I don't know, maybe you try to go to the supermarket at lunchtime because this is a larger, higher priority task. And maybe you try to do a smaller task, get some Duolingo in a coffee break, maybe something like that. What's nice about this approach, like the polling server approach, is it does not affect the ability of the system to complete the hard deadline tasks. because the background server's execution time is known and predictable. The background server runs following a schedule that we understand what it is and what it does and when it's going to run, and we can accordingly be sure that other hard deadline tasks are going to complete, and the non-hard deadline tasks just go in their little container, and they run when they are able to. The downside of this is the response time for aperiodic tasks can frequently be kind of worse, right? It is half the server period plus the average execution time, and the only way to improve that is to make the server period shorter, which might not actually be desirable because it increases the overhead of running this significantly. Okay, and we'll take our current understanding of this aperiodic server, and we're going to build it up and add little improvements until we get to kind of a final version that is going to be as good as it can get. So variant 1 that we're going to talk about is called the Deadline-Deferrable Server. And it's an improved version of what we've seen, and it gives better performance for aperiodic tasks, and it's called deferrable because instead of throwing away the time budget if it's unused at the end of the period for the aperiodic tasks and there's nothing to do, we save that leftover time in case something else arrives. Eventually the period expires, and at that point the remaining execution time is lost, or the execution time is exhausted by actually doing tasks. So to put some numbers on that to try to make it make more sense, in the polling server situation, if we run out of things to do with 40% of its time budget available, the polling server ends and the remaining 60% of that budget is thrown away. In the deferrable approach, then we save that, and the budget is retained until the end of the period for the deferrable server. So if something comes in during the remaining window, it can start immediately. The advantage here is effectively that an aperiodic task will likely be served faster than it would have been if it arrives later. So I want to sort of continue the lunch analogy to try to make that make more sense. Let's say you have an hour for lunch and you finish eating in 45 minutes. In the polling server approach, you go back to work even if lunch is finished in 45 minutes, and even if your extra lunch break time isn't used up, those extra 15 minutes are discarded. You just lose them. Back to work, peasant. In a deferrable server, your extra 15 minutes of lunch time isn't used up, and you could use those 15 minutes later on in the day for something. Take a personal call, do a language lesson, whatever it is. That doesn't, however, carry over to the next day. Right? The next day you get another full hour for lunch, but the extra time from the day before didn't carry over. So in the deferrable server, you can save those 15 minutes for today, but tomorrow everything is reset. You're back to zero, whether you had unused time or not. It all goes back to the beginning. With that said, none of this is a substitute for legal advice from an employment lawyer about the rules and regulations around legally required breaks during the workday. So please just take this analogy for what it is. It's me trying to explain to you the deferrable server thing in a relatable way, and I don't want you to think that somehow this is legal advice around what you can do with your lunch break and when lunch breaks happen at your co-op job. Okay. Next idea. Variant 2 is called the Deadline-Sporadic Server. And the next idea for a high priority task that handles these aperiodic tasks is like Deadline-Deferrable, but instead of, two things. Right? Instead of losing any extra unused period, it can be saved for the future indefinitely. And number 2, there's periodic replenishment of the budget such that it forces execution to be spread out more evenly. Okay, we'll have to explain that a little bit to make it make more sense. Why does spreading out the execution matter? So the deadline server, as it's been defined so far, could theoretically schedule 2 runs of the server back to back, which is very convenient for some aperiodic tasks, i.e. the ones that are currently there and currently ready to execute. But it's not very nice to others. So when I was doing my first co-op term in Toronto, one of the buses that I would take to get to work was Finch West. And the schedule said frequent service, which was TTC speak for every 10 minutes or more often, although we used to say FS was stood for something else, the second word of which was sucks. This bus running along Finch West was subject to a phenomenon which in the transit literature is called bunching. And that means you could stand at a bus stop for 30 minutes and then 3 buses would arrive and then no more for the next 30 minutes. And yet, on average, there's a bus every 10 minutes, right? But it's very frustrating. This is convenient if you happen to be standing at the bus stop at the time when 3 buses arrive, because you can get aboard the least busy one and ideally have a fairly pleasant ride as much as is possible, traveling on a TTC bus during rush hour. But you might be very unlucky if you've just missed it and now you have to stand at the bus stop for 28 minutes. Then you might not be very happy about that. And I mean, it was a summer term, so the weather was okay. So if I did have to wait a long time for a bus, it was just like, all right, I guess it's kind of hot out some days, but it wasn't the end of the world. This could have been much less pleasant had it been a winter term, let's say. There's a lot of explanations, again, in the transit nerd literature about why bunching happens. And to a certain extent it happens because adding passengers and passengers getting off the bus takes time. So the bus in front slows down because they have to let people on and off. Whereas the bus behind, because the bus has recently been to the stops, doesn't have to stop as much. And so the buses sort of eventually catch up with each other and they end up bunching. It's what happens when the route is too long and traffic is bad and the TTC is... We could do a whole lecture on the problems of the TTC, but I don't think it's very relevant to real-time operating systems now, is it? Okay, so the same thing could happen with the periodic server, right? That because these are real-time tasks, you could schedule them sort of back-to-back if you wanted, and it doesn't spread out the aperiodic task execution quite the way that you want. And to make that work for the replenishment model, what we're going to do is say that execution time for the server is broken down into chunks. When there's something to do and the server runs an aperiodic task, the amount of time that it runs is deducted from the available budget. The decrease can be in fractions of a chunk, so if there's 10 chunks total, the budget is full, and an aperiodic task runs for 1.5, and the budget is now at 8.5 chunks. When a chunk is depleted, it's scheduled for replenishment at a fixed time in the future. And that spreads out the replenishment such that, we get back another chunk after X amount of time. And if all chunks are exhausted, the server is suspended until the next period. This sort of model might actually be slightly familiar, right? It works for database credits for Amazon AWS database instances. You start out with some number of credits, and they are depleted by using CPU time above a certain threshold. When you do so, right, the number of credits that you have decreases, and they are replenished at a steady rate over time, but also there's a cap, so you can't stockpile too many credits. If that doesn't seem familiar, I'm going to talk about Duolingo again. If you're not actually familiar with Duolingo, we saw his mascot earlier, Duo, the green owl, who occasionally sends threatening notifications on your phone. But you start with 5 hearts, which is also the maximum number of hearts. And if you don't pay for the super unlimited hearts, right, if you make a mistake when doing an exercise, you lose a heart. And if you run out of hearts, you can't continue. You can practice to earn hearts, but right, you have to refill hearts. And hearts refill at a rate of about 1 every 4 hours. You can pay money to avoid this. But in Duolingo, right, the hearts only decrease if you get an exercise wrong. The kind of thing that we're talking about with a periodic server is any actual execution does consume hearts. But this idea of periodic replenishment does exist also in other contexts. Now, of course, most other contexts are not trying as hard as Duolingo to get you to spend money, so you can buy their premium subscription, whatever. But I think it's fair to say probably AWS is trying really hard to get you to spend a lot of money. So there is that. Let's talk also about a third variant. And the third variant is called the Deadline-Exchange Server, and it's built on this Deadline-Deferrable server, but simplifies the idea of handling the chunks. Right? If we said there are 10 chunks, they require some individual tracking, so there's overhead of keeping a handle on, okay, this one is scheduled for replenishment at this time, and that schedule is this one is scheduled for replenishment at another time. That's annoying, because if you have a large number of chunks, we have basically n timers for n chunks to try to figure out when they get replenished. This approach is a little bit simpler. So what it says is that any remaining execution time is discarded when the request queue is empty, and the wait for replenishment is just based on the last chunk of execution time used. It's simple to implement because there's only ever one replenishment to track, and you are always replenished all the way back to full. So that makes it a little bit simpler in terms of accounting. Simulation studies show, just to give you kind of an overview of the various aperiodic server approaches, that they work, but they're different in terms of their effectiveness for different workloads. The paper that introduces the whole idea says that you get good average response time by making the period of the server the same as the shortest of the regular periodic tasks. But it's possible to have different servers configured for different kinds of tasks so that you get the performance that you're looking for. You can customize as much as you need by having effectively arbitrarily many of these. Right? You choose what gives you the best balance of prioritization and performance.